Okay, so the last time we met, we started speaking about integrals of the form sine to the m of x times cosine to the n of x. And we dealt with only one case. We dealt with the case where the exponent of the sine was odd. And we spoke about how to go about working problems like this. The technique is to factor out sine x, replace the remaining powers, of cosine squared of x. Sorry, replace the remaining powers of sine squared of x by 1 minus cosine squared of x. And then let u be sine x. And I gave you one example of that in class. And then I said, well, suppose that the power of the cosine is odd. All right, so if n is odd, then there's a similar rule. So what you do is you factor out cosine x, and then replace the remaining powers of cosine squared of x by 1 minus sine squared of x. All right, actually, I just noticed that when I gave you the first rule, when m is odd, I made a bit of a mistake here. I said replace the remaining powers of sine squared of x by 1 minus cosine squared of x. I said let u be sine x there. U should have been cosine x. But in this second one, where n is odd, you're going to let u be sine x. All right, so I gave you an example of the first case. I'll give you an example of the second case and some variations on it. So suppose I asked you to find the antiderivative of sine squared of x times cosine cubed of x, like this. Here you see the power of cosine is odd. That's cosine to the third of x. So the technique says, or the rule says, if you have an odd power of cosine, what you should do is you should factor out a cosine. So you factor out cosine of x, and then you're left with cosine squared of x, like this. And then it says replace the remaining powers of cosine squared of x by 1 minus sine squared of x. So this becomes sine squared of x. And I'm going to replace cosine squared by 1 minus sine squared of x. And then I still have cosine of x over here. And then the method says, well, you know, it's very simple from here. All you have to do is let u be sine x. All right, so if I let u be sine x, then this integral becomes, and I'm going to switch to the second page now. All right, so this integral, so if you let u be sine x, then the du is going to be cosine x dx. And that is there, right? Cosine x dx. And the integral becomes the integral of u squared times 1 minus u squared du. And since there is no product rule, we want to get rid of the product here. And the way to do that is to just multiply out. So you get u squared minus u to the fourth du, like this. And then the rest is easy. The antiderivative of u squared is u cubed over 3. The antiderivative of u to the fourth is u to the fifth over 5 plus c. And then you replace u by sine x. So this becomes sine cubed x over 3 minus sine to the fifth x over 5 plus c. And that's the end of it. If the original problem was the integral of sine squared cosine to the fifth of x, so I'm not going to write out the next solution fully, but I just want to illustrate what happens if you had something like this, cosine to the fifth x. So you would again factor out cosine x. And then you would be left with cosine to the fourth x here. And the rule tells you what to do. You have to replace the remaining power. Yes, question? Question? All right, if you have a question, you're just going to have to call it out because I can't see you raising your hands or anything. All right, so so what you can do is you can replace the remaining powers of cosine squared by 1 minus sine squared. But cosine to the fourth is the same as cosine squared all squared, like this. And so this becomes integral sine squared, and I'm going to replace the cosine squared by 1 minus sine squared. But the whole thing is squared times cosine x dx. And then if you were to let u be sine x, you would again get du is cosine x dx, and it's there. And this integral would become
Professor, where do you get the negative sign? Negative, I mean, 1 minus sine x squared?
1 minus sine squared x. Where did I get that from? Is that your question?
Yeah.
Okay. It's a trig identity that sine squared of x plus cosine squared of x is always 1. So whenever you see sine squared, you could replace it by 1 minus cosine squared. Whenever you see cosine squared, you can replace it by 1 minus sine squared. Now, in the next couple of days, the techniques that we give will all require the use of trig identities. I'll point out the trig identities that you need. You don't have to memorize them. I'll give them to you on any exam that I give you. And so you'll have them available to you. The only thing you'll really have to know for the exams is, how do you do this problem? How do you do that problem? What are the techniques involved? Okay, so getting back to this integral, if you let u be sine x, then this becomes u squared times 1 minus u squared squared du. And here there are a couple of ways of doing it. You could, if you wish, square out 1 minus u squared. In other words, multiply 1 minus u squared by itself. And you're going to get 1 minus 2u squared plus u to the 4th. And then you just multiply out and integrate term by term. So then it's pretty much the same as the last example. Integrate term by term. All right, so I'll just, leave that as etc. for you, because it's basically the same idea. I just wanted to point out what would happen if you had a power higher than cosine cubed. Okay, I should point out that sometimes you may not get an integral that fits this this format exactly, but can be transformed into this format. So, for example, suppose I asked you to integrate e to the x sine cubed e to the x dx. Now, this doesn't look like one of the forms that I've spoken about, except that you see the sign is being raised to an odd power. So maybe we could use the rule, but we have to get it into the right form. This e to the x is throwing things off. So what you could do is you could try making a substitution and seeing if this integral can be transformed into something easier. So the sensible thing to do here is to let u be e to the x. And then this term here becomes sine cubed of u. But you can't integrate sine cubed of u unless you have a du there. So if u is e to the x, then you can compute du. That's just e to the x dx. And it happens to be there. So this just becomes the integral of sine cubed of u du. And now it's in the right form. You have an odd power of sine. So I'm not going to finish this. I'll just, start it for you. So you factor out sine of u. And then you're left with sine squared of u. And you replace the sine squared of u by the identity that I pointed out to you. You replace sine squared of u by 1 minus cosine squared of u. And then you let u be cosine of x. And then du will be minus sine x dx. What I should have said, let z be cosine of u. All right. The variable here is u. Let z be cosine of u. And then dz is going to be negative sine u du. Okay. Sorry about that. I had the wrong variables there. All right. And so if you do this, this integral just becomes, we're missing a negative sign. So we put in a negative sign on the inside and compensate by putting a negative sign on the outside. And this becomes 1 minus z squared dz. And then the rest is easy. The antiderivative of 1 is z. The antiderivative of z squared is z cubed over 3 plus c. And then it just replaces z by cosine of u. And then it just replaces u by what it's equal to, which is e to the x. And you get the answer in terms of x like this. So you have this recipe that you can follow that will work for you whenever the power of sine is odd or the power of cosine is odd. You can always get the answer very easily by just following the recipe. Okay, now there's only one other case that's easy here. And that is, suppose the exponents of both the sine and the cosine are non-negative integers. So suppose m and n are non-negative. And here's the key here, even integers. And so both m and n are even. Okay, then the following recipe will work for you. You replace, now these are trig identities. If you're asking where they come from, these are just facts from trigonometry that you may or may not have seen. Okay, so then replace sine squared of any angle by 1 minus the cosine of twice the angle over 2. And cosine squared of an angle by 1 plus the cosine of twice the angle over 2. So if you took a detailed trigonometry course, you might have seen these. If you took a pre-calculus course, you might have seen these. If you've never seen them, then just accept this as fact. All right, so let me give you an example of this. Suppose I asked you to integrate sine squared of 5x. Okay, so this is an even power of sine. If you're asking, well, what about the cosine? Where's the cosine? Well, you could think of this as cosine to the 0. 0 is an even non-negative integer. So this integral follows the format where the powers of both sine and cosine are non-negative even. And according to the rule, all I have to do is this. If I see an even power of a sine of an angle, I have to replace the sine squared of the angle by 1 minus the cosine of twice the angle over 2. All right, so I'm going to use that. And I'm going to replace the angle here, the sine squared of the angle, by 1 minus the cosine of twice the angle. So if the angle is 5x, then twice the angle will be 10x. And all this is divided by 2. And the question that comes up is this any better than what we started with? Is this easier to work out? And the answer is, it really is easy to work out, because when you divide by 2, it's the same as multiplying by 1/2. In other words, you could write this as 1/2 of 1 minus the cosine of 10x. And the constant 1/2 can be pulled outside the integral. So this is 1/2 integral 1 minus cosine of 10x. And the integral of 1 is easy. If you integrate 1, you just get x. And if you integrate cosine of 10x, and anybody want to tell me what happens when you integrate cosine of 10x? Somebody just call out the answer.
Is it negative sine x or negative sine?
Right?
Wait, you said
Integrate.
It should be 1/10 sine 10x.
Yeah, that's what it would be. It would be
oh, okay.
sine 10x over 10 or 1/10 sine 10x. Right, so this would be sine 10x over 10, like this, plus.
Why would it not be negative sine?
All right, because the derivative of sine is cosine. Remember, we're taking antiderivatives, right? So an antiderivative means that when you take the derivative of this, you have to get this. And if you take the derivative of sine 10x over 10, all right, let me just show you that as a separate computation, not part of the notes. So let me just, suppose I gave you this sine 10x over 10. This is really the same thing as 1/10 sine 10x. Now, if I want to take the derivative of this, the 1/10 stays. And the derivative of sine of 10x is cosine of 10x times 10. This 10 cancels with this 10, and you're left with the cosine of 10x.
Oh, okay.
So the
Thank you.
derivative of sine 10x over 10 is cosine of 10x, which means the antiderivative of cosine of 10x, right? So the antiderivative of cosine of 10x will just be sine 10x over 10. You get it? Marvin?
Thank you. Yeah, I appreciate it.
Okay. All right, so let me just dump that. All right, so let me give you a different example, which is a little bit more involved. Suppose I asked you to find the antiderivative of sine squared 9x times cosine squared of 9x. All right, so both the powers of the sine and the cosine are even here. And we have to use both of the identities that I pointed out to you. So when you integrate, or when you rewrite sine squared of 9x, you could rewrite that as 1 minus the cosine of twice the angle. So double of 9x is 18x divided by 2. So that's what happens when you replace sine squared of 9x. In a similar manner, you can replace cosine squared of 9x by 1 plus the cosine of twice the angle. So 1 plus cosine of 18x over 2. And this looks worse than what we started with. But actually, it's not so bad. Because if you multiply out 1 minus the cosine of x times 1 plus the cosine of x, that's like multiplying a minus b times a plus b. And you end up getting a squared minus b squared. So if you multiply 1 minus the cosine of 18x times 1 plus the cosine of 18x, you end up getting 1 minus cosine squared of 18x. And then if you multiply the bottoms, 2 times 2 is just 4. And from here, there are a few ways to go. You can replace 1 minus cosine squared of 18x by something simpler. Since sine squared plus cosine squared is always equal to 1, what's another way of writing 1 minus cosine squared of 18x?
Sine square 18x.
Yeah, sine squared of 18x. So this would be sine squared of 18x divided by 4. And this is really the same as 1/4 sine squared of 18x. And you can pull out the 1/4. So this becomes 1/4 integral sine squared of 18x. And now where do we go from here? Well, this is sine raised to an even power. And we already have a rule for working with sine raised to an even power. And that is you're going to replace sine squared of the angle by 1 minus the cosine of twice the angle. 1 minus 36x divided by 2 like this. All right, and then of course, dividing by 2 is the same as multiplying by 1/2. So you can pull out the 1/2, and this becomes 1/4 times 1/2, integral of 1 minus cosine of 36x. All right, so 1/4 times 1/2 is just 1/8. All right, so this becomes 1/8. Integral of 1 minus cosine of 36x. And the integral of 1 is just x. And the integral of cosine of 36x is
Sine 36x divided by 36.
sine 36x over 36. All right, like this, and then plus c. And then you're all set.
So, Professor, on the previous page,
Mm-hmm.
how
Yeah,
did
previous
1
page.
minus cosine square 18x become sine square 18x?
It didn't. There's a 1/4 in front. You see it here?
Yes.
All right, so you were asking me this question. You were asking me, how did 1/4 sine squared of 18x become sine squared of 18x? Is that
No.
what was your question?
No, I'm talking about here. 1 minus cosine square 18x. How did it become sine square 18x?
Oh, this line here?
On the second line.
This, yeah, okay. All right, so let me just show you that briefly. In general, sine squared of any angle plus the cosine squared of that same angle is always equal to 1. So if you were to solve for the cosine squared of an angle, what you'd have to do is subtract sine squared from both sides, and this becomes 1 minus sine squared of the angle. All right, in a similar manner, if you were to subtract cosine squared from both sides of the first identity, you get sine squared is equal to 1 minus the cosine squared of the angle. Okay. So here I have 1 minus the cosine squared of an angle. And according to this, 1 minus the cosine squared of an angle is equal to the sine squared of the angle. So 1 minus the cosine squared of 18x would just be sine squared of 18x. Now, Simondip, I don't know if I'm answering your question or not, so keep pushing me if I haven't
I
answered it.
understand now.
You okay?
Yeah, I understand now. Yeah.
Okay.
Thank
Right.
thank you.
Okay. All right. So that's all there is to dealing with sines and cosines. There are only two cases that we talk about where one of the exponents is odd, or both of the exponents are positive or non-negative even exponents. All right. So I have to warn you about one thing. If I gave you sine squared of x over cosine squared of x, you might think that you should replace the sine squared of x by 1 minus the cosine of 2x over 2, and the cosine squared of x by 1 plus the cosine of 2x over 2. Okay, this is not the right way of going about it. All right, this is not, it's not correct. All right, it's not correct to write this as 1 minus the cosine of 2x over 2 over 1 plus the cosine of 2x over 2. I wouldn't say it's not correct to write it. It's not helpful. Right? It's not helpful to write it like this. And you might say, well, why not? I mean, you just said to us that when you have an even power of sine and cosine, you have to use these identities that you pointed out to me. Right? And the answer to that question is, I told you that you had to have sine to a power times cosine to a power. All right, so we needed this. We needed sine to a power times cosine to a power. And both powers, m and n, had to be non-negative. Even. For this method to work. Now, if you look at what I gave you sine squared of x over cosine squared of x. And if you were to write this as a product, this would be sine squared of x times cosine of x to the negative 2. And here the exponent is negative 2. And the method that I gave you was only for non-negative integers. All right, so this is not going to work. Now, is it possible to do this integral that I just gave you here? I mean, sine squared over cosine squared? The answer is yes, but you have to use a different trig identity. And that's something that's coming up soon. So you only have to know two cases. You have to know when one of the exponents is odd, or when both of the exponents are non-negative even integers, and you're multiplying the sine by the cosine. Or sine to some power times cosine to some power. Okay, so what's the next thing in this list of trig integrals that we have to deal with? The next thing is this, integrals involving powers of secant and tangent So we're dealing with integrals of this form. Integral tangent to the m of x times secant to the n of x dx. And we're only going to take the cases where m and n are positive integers or 0. Now these are trickier than they look. But there are certain rules that we follow when we see an integral like this. For most of these integrals. You factor out secant squared of x or tan squared of x or secant x tan x, and then use the trig identity that 1 plus tan squared of x is equal to secant squared of x. Sometimes parts helps. So integration by parts. All right, so what I'm going to do is I'm going to give you several examples now. And what we do now and what we're doing today is going to build on what we do next time. So these integrals turn out to be pretty important in what's coming up. All right, so let's start with a simple case. All right, so simple case. Suppose I asked you to just integrate tan of x. Well, some of you may have seen this in Calc 2. There is an identity involving sine, cosine, and tangent. And that identity is if you take sine x and divide by cosine of x, you end up getting tan of x. Now, it's not obvious that this is going to be the identity that helps you to do this problem, but it turns out that this is what helps. All right, so you could write tan x as sine x over cosine x. And then, so something sort of jumps out at you. You can make a substitution here that will make this integral pretty easy. You could let u be cosine of x. And then du will be negative sine x dx. And the only thing that you're missing is the negative sign. So it's the usual thing that you did in Calc 2. You put in a negative sign, you multiply on the outside by a negative sign, and this becomes negative integral du over u. And that's a standard integral from Calc 2. And if you integrate du over u, you get natural log of the absolute value of u plus c, and then you just have to replace u by what it's equal to, which in this case is cosine of x. All right, so if you want to find the integral of tan x, it turns out to be negative natural log absolute value of cosine x. But if you want to go further, if you want to put this in another form, you could do this. You could realize that the negative in front is really -1, like this. And one of the rules for logs is that multipliers in front of a log can be turned into exponents. So this becomes natural log of the absolute value of cosine of x, all raised to the -1 power. And don't confuse this with arc cosine. We're not talking arc cosine here. We're talking about cosine of x being raised to the -1 power, which is really the reciprocal of cosine of x. So this is 1 over the absolute value of cosine of x. And you may remember that the reciprocal of the cosine of x is the secant of x. So another way of writing this integral is that this is the natural log of the absolute value of secant of x plus c. In a sense, this is a little easier than the original one. But that's how it's done.
Professor, can you put the paper up just a bit?
Can you see it? Or not?
Yes, thank you.
Okay, so let me go to the next simple case. All right, so the next simple case, we just integrated 10. And so the next thing that we want to do is we want to talk about, well, what happens when you integrate secant of x. This integral first occurred in map making. So if they could find this integral, it was going to be useful to them. It had a practical application, and they were interested in finding the solution to this. Now, anybody want to take a shot at how to do this?
Does that say secant?
Yep.
Considering that secant x from the previous example, can we rewrite this as 1 over cosine x? Is that like helping anyone?
All right. Now that's what most people say, and I'm gonna leave this sheet the way it is for the moment and come back to it. But I'm just gonna follow your thought process with a different sheet of paper.
Professor,
So you were suggesting,
Professor?
Yeah.
I don't know if I'm right or wrong, but I think there's one more identity of the sec, which is 1 plus 10x or something like that.
1 plus tan squared is equal to secant squared. That's the identity, and
Okay.
that doesn't quite help you.
Oh.
So
Is
suggestion,
it cos x by sin x, something like that?
no, secant of x would be 1 over cosine of x, so that was the suggestion that was made. And then the question became, well, does this help? So most people would say, well, why don't you try making a substitution? Why don't you let u be cosine of x? And then this is just 1 over u, but that's not enough, because in order to integrate 1 over u, you need a du there. And the du for cosine of x is negative sine x. And it's not there.
Professor, then how about multiplying and dividing something so that it gets to secant square or something?
All right, so that's what we're going to be talking about. So this is the logical thing to do, to write secant as 1 over cosine and then try making a substitution, but it doesn't work. Well, it turned out that this integral was harder than people thought. And pretty soon it became like a contest problem. And there was a prize given for whoever could find the integral of secant of x. And finally, after quite a while, somebody came up with a clever solution to finding the integral of secant of x. This is not obvious. I don't know how this person thought of this, but the person said, let's rewrite secant of x another way. All right, we're just going to multiply secant of x times 1. And of course, that's nothing clever. Secant of x times 1, of course, is secant of x. But then here's where the clever part came in. He said, write 1 this way. Write secant of x as secant of x over 1. And write 1 as secant of x plus tan of x, all divided by secant of x plus tan of x. Now this looks like things are going in a bad direction here. All right, so if you multiply out on the top, secant of x times secant of x is secant squared of x. And then distributing the secant to the tan, you get plus secant x tan x. And then on the bottom, you have secant x plus tan x. And this is looking pretty miserable. All right, so then he said, well, now make a substitution. Let u be the denominator here. Let u be secant of x plus tan of x. And let's work out the du and see if it's there or not. So of course you have to know your derivatives in order to work out the du here. So the derivative of secant x is, anybody remember?
Secant x.
Tan x.
Yeah, secant x tan x. And the derivative of tan x is,
Secant square x.
yeah, secant squared x. So the du is secant x tan x plus secant squared x dx. Do you see that anywhere in this integral?
The numerator.
Yeah, the numerator. It's just that the two pieces are reversed. It's the same thing as the du, but the secant squared is written first instead of the in the numerator, the secant squared is written first, whereas in the du, it's written second. So this integral just becomes the integral of du over u. Now this was really brilliant. And so this would just be natural log of the absolute value of u plus c, and what's u in this case? Well, u is just secant x plus tan x. So this becomes natural log of the absolute value of secant x plus tan x plus c. All right, so this is an integral that's going to come up a few times. You might want to memorize this. Okay, so let me take some other cases now. Suppose I wanted to find the antiderivative of tangent squared of x. Well, there is this identity that I pointed out to you earlier when you deal with these integrals. And the identity is that 1 plus tan squared of x is equal to secant squared of x. So if you use that identity, and if you solve for tan squared of x in terms of secant squared of x, you get tan squared of x is equal to secant squared of x minus 1. Now, does this help any? Well, let's see. If you remember your derivatives from Calc 1, secant squared is the derivative of one of the functions, one of the trig functions, and
10x.
yeah, 10x. So the integral of secant squared is just 10x, and the integral of 1 is just x plus c, and we're all set. Okay, so this involved the trick of using the identity and 1 plus tan squared equals secant squared, and then using the fact that secant squared had an antiderivative, which we knew. Okay, so now we get to the higher level questions. I suppose I asked you to find the antiderivative of tan squared of x times secant to the fourth of x. Okay, so whenever you have these problems, I pointed out to you that usually what happens is you either factor out a tan squared, you factor out a secant squared, or you factor out a secant tangent. But then you want to use the relationship that 1 plus tan squared equals secant squared. So you're always going to be using this relationship over here. Okay, so if you were to factor out secant x tan x, then you would get tan raised to an odd power and secant raised to an odd power. Once you factor out the secant x tan x. And this identity would not be useful to you because this involves only even powers of tangents and secants. The other thing I said you might try doing is factoring out tan squared. Well, it's already factored out for you. And that doesn't suggest any way of proceeding with this problem. So that's probably not a good idea. So the only thing left is maybe we should factor out secant squared. So let's try that. Okay, now the method that I pointed out to you said, all right, so once you do this, once you factor out one of these things that I suggested you factor out, you're going to have to use the relationship that 1 plus tan squared equals secant squared in some manner, shape, or form. All right, now you know that the derivative of tan is secant squared. So that suggests making the substitution u equals tan x here. But then I have to worry about this other secant squared on the end. I want to express it in terms of tan if I'm going to make the substitution u equal tan x. So here's where you use the relationship. Okay, the relationship is that you have to use 1 plus tan squared equals secant squared somewhere along the way here. All right, so I'm going to use it over here in this thing in parentheses. I'm going to replace the secant squared of x by 1 plus tan squared of x. And now I'm going to make a substitution. I'm going to let u be tan x. And then du will be secant squared of x dx. And it's there. Secant squared of x dx is there. Okay, so if you make the substitution, tan squared just becomes u squared, and the secant squared dx is just du, and 1 plus tan squared is 1 plus u squared, and now we're in the same boat we were before, where we have a product, but it's a very simple product, and it's easy to integrate if you multiply out. So this becomes the integral of u squared plus u to the 4th. When you multiply out. And the antiderivative of u squared is u cubed over 3. And the antiderivative of u to the 4th is u to the 5th over 5 plus c. And in this case, u is equal to tan x. So this becomes tan cubed x over 3 plus tan Tan x to the fifth over 5 plus c, and we've got the antiderivative. Okay, let's do another one. Suppose I want to find the antiderivative of tan cubed 8x times secant cubed of 8x dx. So you have to keep in mind that we're going to be using this relationship that 1 plus tan squared equals secant squared in some form. So you either want a secant squared to be there or you want a tan squared to be there. And you can accomplish that by factoring out secant 8x times tan 8x. So if you factor out secant 8x times tan 8x, you're going to get tan squared of 8x times secant squared of 8x times secant of 8x tan of 8x dx. And in all these problems, what you factor out is usually the du or something very close to the du. So in this case, I factored out secant x, secant 8x tan 8x dx, and that should suggest to you that that's the derivative of some function or something close to the derivative of some function. And again, if you know your derivatives, the derivative of secant is secant tangent. So the derivative of secant 8x tan, so if you wanted to find a function whose derivative is secant 8x tan 8x, it would be related to secant of 8x. So if that's going to be the du, then u is going to have to be like secant of 8x, and that requires that the integral be expressed in terms of secant of 8x. So that tan squared of 8x is in the way. But what I can do is I can replace tan squared of 8x by secant squared of 8x minus 1 using the identity. We're using the identity that 1 plus tan squared equals secant squared. So tan squared is secant squared minus 1. All right, so this becomes secant squared of 8x minus 1 times secant squared of 8x times secant 8x tan 8x dx. And now, making a substitution makes the problem much easier. You let u be secant of 8x. Then du will be secant of 8x times tan of 8x times the derivative of 8x, which is 8, which I'll put in front. So the derivative of secant of 8x is 8 secant 8x tan 8x dx. And the only thing that you're missing is the 8 for the du. So you put in the 8th and you multiply on the outside by 1/8. And this becomes 1/8, the integral of, instead of secant squared 8x minus 1, it's u squared minus 1. Because u is secant of 8x. And again, the secant squared is just u squared. And we just put in the 8. So on the end, I have 8 secant 8x tan 8x, which is just du. And then we're back into the same boat again. Here. We have a thing that we can integrate if we multiply out. So we multiply out, we get u to the 4th minus u squared du with a 1/8 on the outside. And that becomes 1/8. Antiderivative of u to the 4th is u to the 5th over 5. The antiderivative of u squared is u cubed over 3 plus c. But what's u in this case? In this case, u is equal to secant of 8x. So this becomes secant of 8x to the 5th over 5 minus the secant of 8x to the 3rd over 3 plus c. Okay, so if you look at the last 2 examples that we did, from the last 2 examples, if secant and tangent are raised to odd powers, factoring out secant x, tan x seems to help. If secant is raised to an even power, factoring out secant squared seems to help. So if you want, you can kind of use these as guidelines. Or you can just try the different methods that I pointed out. You know, either factoring out tan squared or factoring out secant squared or factoring out secant tangent and seeing what works best. Okay, so this stuff is quite technical. Takes a while to get used to how to do these problems. I do want to give you another example, but I don't have time to give you another example. So let me give you the homework for Thursday, and on Thursday we'll go over today's homework also. Okay, so I'll copy these sheets and I'll send them to you. So today is Tuesday. Okay, so page 332. Numbers 4, 6, 15, 20. I'm going to give you the hint here. Factor out tan squared. And then question number 24. Okay, now 15, you have to use some trig identities, but maybe you'll see it, maybe you won't. If you see it, great. If not, so you'll learn from the homework, and next time you see it, you'll know how to do it. All right. Okay, so that's it for today. Thanks for showing up. I know this is difficult doing things remotely. I don't like it. I'm sure you don't like it. I'll see you folks on Thursday. Okay, and I'll send these things out to you today. Okay, so that's it. Take care. See you.
Professor,
Yes.
When is our first exam?
All right, now, I was planning to give it to you not too far from now. But I found out that there are going to be some fire drills. So that's gonna cut into the time. I will make a decision in the next week about when to give you the first exam. Okay, it's either gonna be the first week in March. That's the most likely time that I'll be giving it to you, or I may give it to you in about 2 weeks or so. I'll have to figure out what works best. I don't want to get caught with the fire drills because that will be a real problem. I can tell you that your first exam will not go beyond what we did today. So you'll have time to let it sink in. Okay, I'll be doing new stuff on
Okay.
Thursday, but that won't be on the exam. Okay, so any other questions? All right, so I'll see you.
So when
Friday.
you will be posting these notes, can you also give us extra problems?
Yeah, I can give you extra problems if you want. That's not a problem. Okay, I'll work that out for you.
Thank you.
Okay, so I'll see you all on
So
Yes.
for
question.
so for the exam, are we gonna get a review sheet or like exactly what topics are gonna be on the exam?
Yeah, I'll tell you exactly what topic's gonna be on the exam. Not gonna be too much. Basically, I'll review this in class with you, but you know, it's gonna be integration by parts. It's gonna be partial fractions. And it's gonna be integrals of secants, tangents, sines, and cosines. That's basically it. Now, you know, these problems
Okay.
are tedious. They take time. So there won't be too many problems, but they will be worth a lot of points. So you're gonna have to know the basics, and you'll get credit for anything you do. Just as long as you're showing me some kind of a knowledge of the material, and I'll give you all the trig identities that you need, so you don't have to memorize anything other than what technique should you use if you had an odd power of sine or cosine, or both powers of sine and cosine are non-negative even integers. So you just have to know the methods.
Okay, got it.
Any other questions? Okay, so I'll see you folks on Thursday.
I need to talk to you like after everyone leave for 5 minutes.
Okay, I'll stay on.
Thank you.
All right, take care, Professor.
Okay, take care.
All right, have a good one, Professor.
Okay, bye-bye.
Yeah, Professor. So I mean, I sent you an email
Right,
yesterday
I got it.
regarding scholarship. So I've wrote the personal statement. So I mean, if you can like read through my personal statement and see if there is some like changes should I made, or is it okay?
Yeah, I'll look it over and I'll let you know if I think any changes should be made. I'll get back to you probably by tomorrow on that.
Sure. And also, like Professor, you since you were not in the last class, so I was just worried if you are okay or if you are.
No,
I
I'm
mean, you were out
okay.
of.
I thought the guy had told you that I needed to be at a conference that weekend. So I didn't want to lose the class completely. That's why I had somebody come in and do the homework. This happens almost every year. I go to a conference once or twice, you know, usually once a semester I go to a conference, and usually I miss one day. So I usually have someone take over, but I don't expect to miss any other days going forward, unless, you know, things happen that I don't anticipate. Okay, but thanks for asking. I'm fine. Okay,
Okay, good. Thank you, Professor. Bye.
okay, see you. Bye-bye.